Hello everyone, welcome to Stat 310 lecture 15. So we're in the middle of this chapter 9 which focuses on hypothesis testing, which is kind of a different framework from estimation where we're trying to kind of get the kind of 0-1 answers or binary answers to particular questions by putting them in a hypothesis testing framework. So we're kind of in the middle of this chapter, and we've spent a lot of our time mainly talking about simple hypotheses where the both the null and the alternative are just one number. So in this lecture, the focus is going to be more on composite alternative hypotheses, and in particular, we're going to actually show that there's this really nice duality between hypothesis tests and confidence intervals. This is in section 9.3 of the textbook. And so what this actually shows us, which is pretty cool, is that a lot of the calculations that we did in chapter 8 for confidence intervals can actually naturally give you a very nice hypothesis, it in some sense a one-to-one correspondence with hypothesis tests. And why this is really cool is that it essentially means that calculations wise there's almost no difference from what you've already calculated in a hypothesis testing scenario to what you've already done when we've looked at estimation and confidence intervals. And this duality will kind of show us why. And it'll also give us a way of going from hypothesis tests to confidence intervals, and then from confidence intervals back to hypothesis tests. Okay, and so the scenario that we'll be mainly in today is the scenario where the null hypothesis is simple. So this is a simple null where theta is equal to theta 0. So that's what we've seen mainly. And in particular, there's 4 alternatives that are pretty standard when we have this is our null hypothesis. One is that the simple hypothesis, which we spent quite a bit of time on in the last lecture or two, which is that the alternative hypothesis is just a single point that's not the point theta 0, so theta equals theta 1. That's a simple one. And then there are 3, and this typically occurs more in practice, that the alternative is a composite hypothesis. And then there's 3 kind of standard composite hypotheses you might look at. There are others you might look at too, but these are the 3 that come up most often. The first one is just that, in some sense, the complement of the null, which is that theta is not theta 0. So theta is all the real numbers except for theta 0. And so this can be viewed as a composite and two-sided alternative. And then the other one is composite one-sided, and there are 2 versions, either theta bigger than theta 0 or theta less than theta 0. And these are also composite and one-sided tests. And the thing we learned in the previous lecture as well is that for simple null hypothesis, we can kind of say that there's a test that we sort of tend to use a lot, which is the likelihood ratio test. And this is the most powerful amongst any test of size alpha. So remember that alpha was this important quantity or parameter that we use to determine the test that we're looking at. And then the question that we're going to start to look at today, and we're also going to look at in the next lecture, is what can we say about alternative hypothesis? So we're going to, not today, but in the next lecture, lecture 16, we're going to generalize the likelihood ratio test when you have composite alternatives and in composite nulls. But today we're actually going to see that in general how to generalize how we can in some sense use what we already know about confidence intervals to say something about tests that we've hypothesis tests when we have composite alternatives. And then also we'll see that you can actually use this idea to actually get new confidence intervals as well. So to motivate this, we're gonna just begin with an example that we're very familiar with now. Okay, so we're gonna start with this example that we often come back to because it's very instructive. So we have x1 through to xn are independent with the normal distribution with mean, mu, and variance sigma squared. We're assuming that sigma squared is known. It's a known positive constant. So it could be 1 or 2, but it's just some number that we know. And then so mu is the unknown parameter of interest. Okay, and so what we're going to do with this example, and then we're going to generalize it later, is we're going to kind of show how what we learned in chapter 8 with finding confidence intervals can potentially be used for to connect to what we've already done with what we've already done with hypothesis tests in chapter 9, and connect some of these concepts. So let's look at from chapter 8. We want to find a 1 minus alpha times 100% confidence interval for mu. Okay, so this should be, from chapter 8. And one thing to note is that this alpha appears here, and note that alpha also appears in that size of the test, and that's going to be instructive because that's going to allow us to connect these two things very easily. Okay, so how do we do that? So we first need an estimate for mu. So the most natural choice is mu hat ml, which is also mu hat mm, which is the most intuitive thing we could think of, which is the sample mean. Okay, so this is going to be our estimate for mu, and then to find 1 minus alpha times 100% confidence interval, we say that you can write this as x bar plus or minus z alpha over 2 times sigma over square root of n. Okay, and so this is a calculation we've already done. So and this is for mu. So another way to say it is that the for mu is just mu is in x bar minus and then x bar plus z sigma over square root of n. So remember, the z-score comes from the normal table, or the z table that we see, or you can equivalently write this as mu. And so I'm going to use this notation as this is a confidence interval, and it's a function of x1, x2 up to xn. So confidence intervals are data dependent because you're using kind of the data to determine them, and you're saying that mu is in this confidence interval. And so another way to think about that is that mu is between okay, and so So this is the thing to remember is the 1 minus alpha times 100% confidence interval for mu in terms of this data x bar. Okay, so now let's look at hypothesis testing, which is what we've done in chapter 9. And we're going to connect these two. So this is in chapter 9. So we have our h naught, which is mu equals mu 0. Here theta equals mu. And we're going to use the alternative, which is this composite alternative, mu not equal to mu 0. Okay, so this is, remember, the two-sided alternative. Okay, so now the question is, we want to do a hypothesis test of size alpha. Okay, so how do we do that? So remember that for a test, we have our null, we have our alternative, we have our size of the test, and then we need a test statistic. And again, we're just going to use x bar because that's kind of the most natural thing to do when we're doing the mean for a normal. And then we also know that the distribution of x bar is just x bar is normal mu sigma squared. So one thing to note is that the distribution, that's sigma squared over n. The distribution of x bar under h naught is okay, and so I just wanted to pause for a second just to point out the differences between these two statements. So x1 through to xn is normally distributed with mean mu and variance sigma squared. So we've kind of learned from chapter 8 that x bar has this, or from even earlier chapters, that x bar has this distribution of normal with mean mu and variance sigma squared over n. But in chapter 9, we've looked at this notion of a hypothesis test. And one of the things that's there is that you're looking at the distribution of your test statistic, but under the null hypothesis. So the null hypothesis is that mu equals mu 0. So that's why these statements are a little bit different. The first statement, x bar is normal mu, mean mu variance sigma squared over n, says that our x bar has the normal with parameter mu, whatever it is, whereas the distribution under the null h0, which asserts that mu equals mu 0, is saying that for a specific point mu 0, x bar is normal with that mean mu 0 and variance of sigma squared over n. Okay, so the next question is we want to find the acceptance region for h naught. So this acceptance region is going to be a really critical concept that we're going to use to connect confidence intervals and hypothesis tests. So remember, the acceptance region is if x bar is in AR, so let me just explain this. This means that then you accept or fail to reject their equivalent. So you accept or fail to reject H naught. And so what this means is that, you know, AR of mu naught, it's the acceptance region as a function of mu zero. So how do we find it? So the size of the test is alpha, and then the alternative is mu not equal to mu zero. So what that basically means is that you would want to find the acceptance region of mu zero is going to basically look like because it's two-sided, you'd kind of expect it to be symmetric. Then what it's going to look like is this region here, AR of mu zero. So it's going to kind of be, you know, these are going to be the two endpoints. And what you want is you want the area in the tails to be alpha, okay? Right? Because you want that the probability that X bar is not in the acceptance region to equal to alpha, and this is under H naught. Okay. So how do we calculate this? So this again just naturally means that the acceptance region of mu naught is going to just be mu naught minus z. You want this area to be alpha over 2 and this area to be alpha over 2 because you have a two-sided alternative here. Mu alpha 2, and then it's going to be sigma over square root of n. Obviously, because we know that and the reason why this is the case is that, you know, we know that under H0, X bar is normal with mean mu naught and variance sigma squared over n. Okay, so therefore the standard error is going to be sigma squared over n, or the square root of sigma squared over n, and that's why we get this. And so let's kind of compare these two. So we have one thing, which is the confidence interval. Which is that going to use this notation C of x1, x2 up to xn, which is just, and you're saying mu is in the confidence interval C of x1, x2 up to xn, where C of x1, x2 up to xn, if we remember from earlier, was just okay, so we have a confidence interval here, and so this is equivalent to saying that mu is between X bar plus z alpha over 2 times sigma over square root of n, and then okay. And so now let's look at we've got now in the acceptance region of a hypothesis test. And so remember that we're going to use the notation here, AR, and this is a function of mu0. This doesn't have data in it, but then we're saying that X bar is in AR of mu0. So this is your test statistic, and so this in our case was going to be mu0 minus z alpha over 2 times sigma over square root of n, mu0 plus z alpha over 2 times sigma over square root of n. And so if we write this out, this is equivalent to saying x bar is between mu0 minus z alpha over 2 times sigma over square root of n, and less than or equal to mu0 plus z alpha over 2 times sigma over square root of n. Okay, and so one thing to note is, let's look at these two regions here. So the thing to notice here is that if we let mu equals to mu0, then we have two statements here from the confidence interval perspective. So the confidence interval, just to step back a little bit here, the confidence interval, you write that the parameter lies in a confidence interval, which is a function of the data. In the acceptance region of the hypothesis test, you're saying that your test statistic, which is a function of your data, lies in some region which depends on your parameter mu0. So you're kind of doing like things in reverse. Like this is why it's a duality, because the confidence interval is a function of your data, and you're saying that your parameter belongs to that function of your data. Whereas in the acceptance region of a hypothesis test, you're saying that you're finding the acceptance. This is a function of your parameter, and you're saying your data lies, your test statistic, which is a function of your data, lies in that region. So let's examine these two regions though. So if we let mu equals mu0, we have that from hypothesis test, or let me say, so from the confidence interval, we have that mu0 is less than or equal to x bar plus z alpha over 2. And mu0 is greater than or equal to x bar minus z alpha over 2 times sigma over square root of n. And if we do some rearrangement, so this is equivalent to if we look at the first example, we can say that this is equivalent to x bar is bigger than or equal to mu0 minus z alpha over 2 times sigma over square root of n. And then the second statement is that x bar is less than or equal to mu0 plus z alpha over 2 sigma over square root of n. All I've done is to just rearrange the above statements. And this is equivalent to x bar is between mu0 plus z alpha over 2 times sigma over square root of n. Okay, and so note that this thing here is this is the same statement as x bar is in AR of mu0. So note that we've started with the confidence interval, right? And I've just broken that up into two parts to get to sort of make this a little bit clearer. And then we've just, doing some rearrangement, got exactly to the acceptance region. Okay, and so note that and we can do the reverse, and I won't do this because it's you can go through the calculations yourself. You can go from x bar is in AR of mu 0, go to mu 0 is in confidence interval of x1, x2 up to xn. So this is essentially the we've kind of demonstrated what's going on in the case of the normal distribution, but this is really going to be the kind of the key equivalence that we see, or duality, not necessarily not equivalence, but duality between the acceptance region of a hypothesis test and a confidence interval. So this leads to the general theorem. And this is in 9.3. And the main, this is calculations wise, there's nothing new here. It's just, this is a useful result because it helps with calculations, but it also kind of puts into context the main concepts and gets your head around like what exactly is a confidence interval, what's the acceptance region of a hypothesis test, and why is there this duality between them. So we're in the scenario where So assume we're in a hypothesis testing scenario with h naught theta equals 0, theta equals theta 0. So we're going to let AR of theta 0 denote the acceptance region for a test of size alpha. And then we're going to let Ci of x1, x2 up to xn denote a 1 minus alpha times 100% confidence interval for theta. So then we have that so then we have the equivalence or duality. That so let so if we let t of x1 through to xn be the test statistic for estimating theta, then t of x1, x2 up to xn in a of theta 0, that is equivalent to theta 0 in the confidence interval defined by x1, x2 up to xn. Okay, and so you can equivalently say that if you're, or I guess you don't even really need this t here. This is just true for, because the t like kind of is implicitly in there anyway. If your data x1 through to xn lies in your acceptance region of theta 0, that's equivalent to the theta 0 lying in the confidence interval of x1 through to xn. Okay, and so that's pretty cool because that just kind of means that if you have a confidence interval, you have the acceptance region of a hypothesis test and vice versa. Okay, and this also naturally leads to the next notion that we're going to talk about, which is one-sided tests and confidence intervals. So now you should be starting to think about hypothesis tests and confidence intervals as one and the same thing, because as we've seen, there's this very nice duality between them. So now we're going to consider the alternative theta bigger than theta 0. And we're going to say, so we have the test statistic t of x1, x2 up to xn. So the test statistic's a function of your data, like the sample mean or something else. And so so we first want to find the acceptance region of theta 0. This is we want a test of size alpha because alpha is this parameter that determines. Now we can see that it determines two things, like the size of the test and the width of our confidence interval. I guess let's be a bit more concrete. So let's just go back to this example, because I think if you understand what's going on in this example, you can kind of easily see how this generalizes to other examples. So if we have x1, x2 up to is normal, mu sigma squared. So you have your h naught, which is mu equals mu 0, and you have your h1, which is now mu bigger than mu 0. Okay, and so we want so we have that our test statistic t of x1 through to xn is equal to x bar. Find acceptance region of mu 0. So remember once again that we're in this sort of nice normal setting where x bar is normal with mean mu and variance. Let me be clear here. Variance sigma squared over n, and then so what that means is that under h0, x bar is normal with mean mu 0 and variance sigma squared over n. And so what that means is that if this is our mu 0, so if our alternative is mu bigger than 0, so our alternative here is mu bigger than mu 0. So what that means is that our acceptance region should actually kind of lie here. So this is going to be the acceptance region of mu0, because you want, and this is going to be of the size of the size alpha, because you want acceptance region is region where you accept null h naught. And because the alternative is saying that mu is in some sense bigger than mu0, it means that therefore the acceptance region has the form that x bar is going to be less than or equal to, and then we can see that it's going to be mu0 and then plus. Now it's going to be z alpha. There's no alpha over 2 because it's one-sided, and then times sigma over square root of n. Okay, so this is going to be our acceptance region. And then we want to hence find a 1 minus alpha times 100% one-sided now confidence interval for mu. Okay, and so you can kind of rearrange this to say that, okay, we have x bar is less than or equal to mu0 plus z alpha times sigma over square root of n. And similarly, that means that we can write this as mu0 bigger than or equal to x bar minus z alpha times sigma over square root of n. So we have this one-sided confidence interval that mu is bigger than or equal to, because we just replace mu0 by mu. So in the confidence interval setting, there's no mu0, but we can just replace mu0 by mu. Okay, and so note that we have this duality. So this is, we have this acceptance region of mu naught, which is just we have this acceptance region for mu0, and then we have this, the confidence interval, which is a function of x1, x2 up to xn, which is mu is in x bar minus z alpha times sigma over square root of n infinity. And the reason for that is because here we're kind of, it's a little bit, it might seem a little bit confusing, but the confidence interval is saying that we're sure that that mu is bigger than a particular value. Now let's do a different one-sided alternative here. So the different one-sided alternative is like, let's say that H0 obviously is that mu is equal to mu0, and that the alternative is mu less than mu0, okay? So in that case, the test statistic is equal to x bar, and so in this case, x bar is distributed to normal. This is all the same as before, sigma squared over n under H0. x bar is distributed normal, mean mu 0 sigma squared over n. Okay, and so so if we want to find the acceptance region of mu 0 in this case, clearly we're going to reject we're going to reject or accept h0 if it's a larger value. So it's going to look like this in this case. So this is going to be our alpha, and this is going to be our acceptance region of mu 0. So it's going to be x bar is going to be bigger than or equal to mu 0 plus z alpha times sigma over square root of n. And similarly, you can see that, so you can rewrite this as x bars in negative infinity okay. And so we want to then find a 1 minus alpha times 100% one-sided confidence interval. For mu. And so we have that x bar is bigger than or equal to mu 0 plus z alpha times sigma over square root of n. And so we can rewrite this as mu. So if we replace mu equal to mu 0, we have that mu is less than or equal to x bar. Sorry, this should be a minus, shouldn't it? Yeah, sorry, this should be a minus here. Is this correct? Yep, this should be a minus, and then this is different. This is the wrong way around. Okay, and so we have that this is a minus. Yeah, it's very easy to get that the wrong way around. So always keep that in mind when you're doing this. Okay, so this is going to be a okay, and so then you know, if we for general theta, if we have a statistic or estimator theta hat, which is, you know, clearly going to be a function of our data, because it's a statistic or an estimator, then you can kind of say that we have like this is equivalent to so the confidence interval is going to be theta is bigger than or equal to theta hat plus z alpha. So we're assuming that theta hat is a normal distribution times some standard error. So this is just the standard error for theta hat. And then clearly the acceptance region is just that theta hat is less than or equal to, bigger than. theta minus z alpha times standard error. Okay, so let's from the acceptance regions of hypothesis tests to confidence intervals and vice versa. Okay, and so I'm just going to put down a table here. So if we've got h naught is theta equals theta 0, and there's three different, and then we also have that our test statistic, I'm just going to use the notation theta hat that we've used before. So I'm going to there's three different alternatives we've considered. So this is the alternative H1. Then there's going to be a corresponding acceptance region of theta 0, and then there's going to be a corresponding confidence interval. So we've seen that there's the two-sided alternative, theta not equal to theta 0, which is what we started with. There's a one-sided alternative, theta bigger than theta 0, and then a one-sided alternative, theta less than theta 0. And for the two-sided alternative, we get theta. So I'm using z here because things are usually normal, but if they're not, you can easily replace this with a different table, like whether it's t or whether it's f or chi-squared or something else. So I've just done, these are just essentially putting the calculations that we've just done onto a table to kind of make it easier to sort of get your head around and think about. Okay, and then similarly, you can get so for each of these acceptance regions, you can also get a confidence interval, which is going to say that theta is in, and remember the difference here is that we're saying theta lies in some interval that's data dependent. So the standard error is kind of gives you the width of this confidence interval. Okay, and so this is just kind of a summary of what we've just seen. So the next topic we're going to look at is how do we generalize the likelihood ratio test to composite or other alternatives? Okay, so this duality that we've just developed kind of shows us a way if we if we have a statistic in mind, how we can go from confidence intervals to acceptance regions and so on. But the likelihood ratio test is what we determined is a pretty good way to do testing. So is there a way we can generalize that? And so it turns out that we can. And this is this leads to the section 9.4, which is the generalized likelihood ratio test. Okay, so we're going to say that H0 is theta is in theta 0. H1 is theta is in theta 1. So these are sets. So these are sets, and they don't have to just be kind of like empty. They don't just have to be one point, as we've seen before. So we have our data, x1, x2 up to xn is distributed with some PDF f of x theta, and they're independent. And so if theta 0 equals theta 0, so this is simple, and theta 1 is equal to theta 1, and this is simple, we simply calculate the likelihood. So if we let likelihood ratio test and we let gamma is the, so I'm going to use this notation that gamma is the likelihood ratio test statistic. That's just L of x1, x2 up to xn theta 0. Theta 1. So this is the statistic. Okay, and obviously we use that statistic to then determine the, I'm going to use, I guess, gamma hat to make it clear that this is a data-dependent quantity. And so we're going to use that to determine the acceptance region. So for general theta 0 and theta 1, we're going to define this GLRT. So GLRT. And then the statistic we're going to use is, it's just an extension of what we've seen, where now we're going to maximize. So it's like we're picking the best option. And then for convenience and convention, it's going to be easier to write theta as in the union of theta 0 and theta 1. We'll see why that's kind of useful shortly. It doesn't really change the calculations too much. So gamma hat is equal to the statistic where we're actually maximizing over the combination of theta 0 and theta 1. So like, how do we find maximum? How do we find the maximum? And so this is where we're going to use the maximum likelihood estimate. So again, the calculations of what we did in chapter 8 are going to be extremely useful here. Use ML estimate. So okay, and then we can write this out as, because we know that the likelihood here is just the product . So this is the how we write out this. So this is the GLRT. So there's kind of two questions that we need to, addresses, so calculating GLRT, and we're going to do most of this in the next lecture. Calculating GLRT, and this is where we use maximum likelihood. And then the other question that we're going to look at is that distribution of GLRT. It'll turn out that this actually has a pretty nice distribution in general that's going to allow us to kind of find acceptance regions and subsequently confidence intervals in a pretty nice, convenient way. So the last thing I'll leave you with is just a specific example. So let's look at one example that we've already seen today, which is H0, which is theta equals theta 0, and H1 is theta not equal to theta 0, or equivalently theta is in every point except for theta 0. So this is like the two-sided alternative that we've already seen. Therefore, we have that so if we look at the GLRT, so let's we want to find the generalized likelihood ratio test statistic gamma hat. So for the numerator, because the null hypothesis is just equal to just that single point, and for the denominator, okay, and so note here that this is just the that theta 0 union theta 1 here is just equal to the real line, because it's just H1 is everything except theta 0, and H0 is theta 0, and that's why including the union here is kind of a convenient thing to do. Okay, and so therefore we can say that gamma hat, because we're maximizing over a single point, this is just going to be f of xi theta 0. And then we have to maximize over the whole real line. Okay, but then what is the maximum over the whole real line, right? All that is just the maximum likelihood estimate. So this is just equal to, and this is going to be equal to the product of I equals 1 to n of what we learned in chapter 8, theta hat ml. Theta hat ml calculated according to chapter 8. Okay, so we have this kind of example where now, although we're maximizing, the maximizing becomes pretty straightforward when we have this scenario where we're looking at this two-sided alternative, because we know that where the numerator is just a single point, the denominator is a maximizer, but we know how to find that maximizer. And so again, if we just plug in the maximum likelihood estimate, we can easily get this GLRT. And we're going to see a couple of examples of this in the next lecture, and we're going to address the question of what the distribution of that test statistic is in the next lecture. Okay, thanks for listening.